Today we're going to talk about watching chemical reactions in real time. And to do that, we're going to need to answer the question, how fast is fast? Well, back in the 60s, Manfred Eigen, Ronald Norrish, and George Porter were awarded the Nobel Prize in Chemistry for their studies of extremely fast chemical reactions affected by disturbing the equilibrium by means of very short pulses of energy. And in this case, extremely fast and very short, that meant things on the microsecond to millisecond timescale. And this allowed them to follow the kinetics of reactions in real time on this microsecond timescale. They could watch reactants going away, being consumed, and products being formed on the timescale of a few microseconds to milliseconds. But if we want to watch reactions in real time, what's a natural timescale for atomic and molecular systems? Well, the natural timescale for motion that leads to a reaction is that of, for instance, a vibrational period. And that can vary depending on the masses of the atoms involved, from, say, 150 femtoseconds down to 7 femtoseconds or so. Or another way to look at the timescale we'll have to probe is, how fast is a molecule? Well, N2 at room temperature travels at a mean speed of about 500 meters per second. And to move something comparable to a bond length, say an angstrom, it would take 200 femtoseconds. In other words, we've got to get down to the ultrafast timescale of a few picoseconds to a few femtoseconds in order to follow chemistry in real time. Previously, we've introduced the processes of photo-dissociation and pre-dissociation. In direct photo-dissociation, we excite to, for instance, a repulsive excited electronic state, and then propagation on that state leads to the breaking of a bond, to dissociation. Or another possibility is that photoexcitation, one of our vertical excitations here, leads to excitation to a bound state, but a curve crossing can mean the molecule passes on to this dissociative curve and undergoes what is known as pre-dissociation. The question now is it possible to follow the dynamics of these processes in real time? Excitation followed by propagation on the excited state potential, breaking of a bond, and then formation of our product. In 1999, Ahmed Zewail was awarded the Nobel Prize in Chemistry for his studies of the transition states of chemical reactions using femtosecond spectroscopy. He introduced the field of femtochemistry, using spectroscopy with these ultra-short pulses to look at chemical dynamics in real time. Now, the first thing we have to recognize is that light is extremely fast. And because of this, we can use small changes in the path length of light to introduce delays between different pulses that we'll generate with our femtosecond lasers. And by controllably varying the path length, we introduce controllable delays between these pulses. Another important thing to remember when it gets to these very short pulses, these ultra-fast pulses, is that there's an uncertainty relationship between energy and time. And getting to very high temporal resolution will mean that we lose some energy resolution. But that we can quantify exactly through this relationship, an inverse relationship between the uncertainty in the wavelength of our pulses and the pulse width. So what were they able to do in Zewail's group? Let's start with the example of ICN. Here we're going to do what's known as a two-color experiment. One color of light will be used to excite the molecule. A second color of light will be used to probe a product. In this case, 306 nanometer light was used to excite the molecule from its ground state to a repulsive excited state. And that sets the initial time T0. Then the system is going to propagate on the upper state potential, the excited state potential, until free product, CN in this case, is formed. And what Zewail's group was able to show was that it took about 205 femtoseconds for the appearance of free CN after the initial photo excitation. But this wasn't enough for Zewail's group. They wanted to see whether they could probe the transition state directly. Let's think about the case of pre-dissociation, where now we're going to take either sodium iodide or sodium bromide in its ground state, excite with the first color, 388 nanometers or so in this case. That will take us up to the repulsive wall of a bound state. Now, sodium iodide and sodium bromide are interesting because they have these two different ways of bonding, either covalently or ionically, right? Which leads to this curve crossing here. So what's going to happen once we form the excited state wave packet? Well, in the excited state, the molecule will begin to vibrate and the bond expands. And then when it gets to the classical turning point, it will return. Now we're going to introduce two different probe lasers. One probe laser will look at the transition state, this area right near the curve crossing. The second probe laser at a different wavelength will look at the product sodium. And what the data shows is something quite interesting and just what we would expect, sort of on those classical ideas of propagation along the excited state potential. What we see is that if we sit here and look for the transition state, we'll see a transient signal form with a characteristic period. If we look for the product, sodium, puff, 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 periodically, puffs of sodium are formed every time the molecule encounters the crossing point, the curve crossing. There's a certain probability that sodium is formed. But it only forms on the way out. On the way back in, the molecule can't fall apart. However, the transition state is formed both on the way out and on the way in. Therefore, the periodicity of the signal of the transient signal of the transition state species is twice the period of the product. So yes, the answer is it possible to follow these dynamics in real time? Yes. Once we introduce ultrafast femtosecond pulse lasers, this allows us to probe chemical dynamics in real time to watch bonds extend after excitation and finally break to form product.